Guten Morgen, everybody. Welcome back to Algebra 2. Sorry, chat. As we look at this, we are going to dig into these guys today. We looked briefly at the calculators yesterday. We're going to go forward with that. Desmos makes stuff a lot nicer to see. For home purposes, if you do not have the Desmos app, I would strongly recommend it. It is way better than your phone calculator, like guaranteed. Probably better than your calculators that you have here, realistically, but we can't use phones in school. So we are trying to look at this. And as we go through, we have only a few different sort of transformations that we're going to deal with. We saw yesterday at the warm-up that there's a transformation that does not change the shape, right? If I have a parabola that lives here, it can move it left or right easily. Now, that has a specific name. When we just simply take an object, we don't change its shape or orientation, and we move it to a different location. Anybody remember what that was called in geometry? It's a translation. So, somewhere in here, there's a translation hidden. Do you remember any of the other transformations? Dilation. What's a dilation do? Bigger or smaller. Now, because we're working with functions and we can't have something that's like a real shape because it can't be closed, that wouldn't be a function, we might have to think about those dilations rather being thinner or thicker, steeper or less steep. That's how we'll interpret it with these functions. Are there any others? Reflection. So within here, we see things that will change the location left, right. We see something that will change the location up, down. We see something that will make it thinner and thicker. And we see something that will possibly make this thing flip over. You guys have probably seen a little bit of this before. Does this look kind of familiar? Yeah. All right. What changes what, just based off of memory?
Like the X minus C is like the translation.
Okay, so Naomi claims horizontal translations. Anybody second that? Cool, maybe. Let's dig in. Now, as we go through, we have this lovely function, and it's actually kind of ugly, right? Is anybody intimidated looking at this? Okay, so we will get over that. It's really uglier looking here than it will be in practice, but it's good to see it in general. We are going to break down each of these into their own little section. So what's the easiest transformation that you guys can think of? Is it easier to move left, right, up, and down? Is it easier to make it thinner or wider and flip it? Which of those three is the easiest? Left and right's the easiest, right? So as we look at this, our first little subtopic within this section, we're talking about transformations. We're going to go ahead and take a look at translations. Now notice all caps. Why? It's a vocab. Now, for our purposes, translate, super easy. It just shifts each point a single direction. Every single point on the graph, all infinity of them, which means we don't change any of our shape whatsoever. So, by definition, we'll just say moves each point. And what are the directions that we can translate in? Not a trick question, I promise. Up, down. So I'm going to say moves each point of f of x. I heard up, down, left, or right. Okay, these are the only four directions that we can translate. Why do I not bother saying, oh, we can go diagonally like this? It's the same thing as going right and up, like they're just those two together. Nice answer there, Ronaldo. Cool. So as we're looking at it, here's how we're going to go with. We can translate two directions. The first direction, we can do it horizontally. And I use H, as I said a second ago, because H for horizontal, but we're using C here, so that's okay. We have horizontal translations, and the flip side would be what? Vertical, obviously, right? Okay. Now, before we dive in, I want to make really sure if you do not have this on your page and you can reference this, because we're going to keep referencing this equation, if you do not have it, you need to write it down on your page because we're going to use this over and over and over and over and over. Cool? All right. So looking at this, Naomi, I think you were right. You guys can play with the calculator and check if you want. If you are comfortable with the calculator, you do not have to have it open. We're going to check here. So what I've done up on the board is, those of you that have not seen Desmos, you can do a ton of really cool stuff with it. And this is just the very beginning. I have x squared up on the board. Now, you can see the red graph, and I've typed in that exact same super duper ugly equation, right? Now, when I turn this one on, all that I've done here is I've put values that we can slide back and forth. They're called sliders on Desmos. So if A is 1, do I really need to write A right here? No. If B is 1, do I really need to write anything with B? No. If C is 0, what does this whole inside turn into? If it's 1 times x minus 0. Try again. What's x minus 0? Times 1? 1x. I like 1x. So this would just be f of x if we simplified it all the way. And then finally, k is 0 because I'm adding nothing to it. This is it right now. They're the exact same thing, f of x and f of x. Cool. So we're just going to play around with it and see what we can come up with. Notice the x minus c. Naomi thinks that if I move this, it's going to move me left and right. So if I pick c to be, I don't know, a positive 2, like maybe we did on the warm-up yesterday, how did it move the graph? So I hear left or right 2. Let's check it. Now, whoa, I should probably turn it on, eh? Boom. All right. So if it's at 0, nothing. And if I move it positive, it moves to the right. Now, there's a natural place where you're going to get goofed up with this. When we say left, it's really natural because we think it goes opposite, right? Here's the weird part of it. If I pick 2.7, this literally reads x minus 2.7. I have chosen the c value that was positive, and it still just shows up as x minus that positive number. Okay, what if I make this negative 2? Or negative 3 or 4? It'll go to the left, and this would change to a what? Positive. So, just to check it, we'll let it ride for a minute. We'll say, hey, what are you doing? And we can see as my c values change, it corresponds directly with a change on the graph here. Nothing too crazy going on. So, we will go ahead and try to summarize this, and let's check it out. If I want to move horizontal, it is the c value, right? Cool. I'm just going to put right here, c, knowing, and I'll change color so it stands out, but knowing that we're just referencing this over and over, this exact same formula. The horizontal in this formula is c. Now, if then statements, have you guys written, you guys have all done proof and all that good stuff, right? Okay. Do you remember using this symbol? Now, you don't have to write this up here, I'm just talking. Can somebody read this to me? And maybe you guys didn't see this last year in geometry. If not, it's super easy. Fred. If P, then Q. Or alternatively, this symbol, it could mean if-then statement, which works fine. But the same statement, just with fancier language, implies. This is an implication. So here we go. On this, I'm just not going to use a mark because I don't want to make it look weird. But if C is greater than 0, how did it move my graph just now? To the right. So C is greater than 0 implies that we move right. How many units? C. C units. Okay. Alternatively, I'm going to say and, just so we can really split the difference. What's the other side of the statement going to be? What if C is less than 0? What did it do? Left, sorry. Now, the super weird part, if C is less than 0, then we move the whole graph left C units. Okay, big warning that I want you to always be aware of. The sign inside of my parentheses switches in this context. So if C is 5, x minus 5 is what you see. If C is negative 2, x minus negative 2, or x plus 2 is what you wind up getting. It goes the opposite when you see it in the parentheses. Okay. Hey, that was a nice transition. What moves me up and down? K. If K is positive, what do you think? And if K is negative? All right, let's check it. So we'll let this one go. We'll just get real crazy. We'll wait first. If K is negative, it goes down. So for example, check it out. At negative 7, how far down did it go? 7. Hey, that's pretty convenient. If K is positive 2, it's going to go up how far? 2. Now, why is it still wonky over here? Why didn't it just go straight up? So, love it. Because I changed C earlier, right? If I change C back to 0 and I put it back where that original parent function was, now I can see this really clearly. This is all that's moving. No shape change, nothing other than up and down. Okay, we're going to get real crazy real quick. We'll do that. And this. And we'll just let it ride for a second. We're going to crash my computer, I'm pretty sure. But we'll get there. All right. I want you guys to help me summarize this then. On your own with your neighbors, I'm going to give you a second. I want you to write the same type of generalization. I'm going to come around and look at your pages a little bit. I try not to hover, but write me a similar statement. What letter impacted this? K, and the dumb device that I use to remember this, K is for vertical, is how I think of this. And I spell it the German way with a K. I usually use H here, so I don't have a good way to say C is for horizontal. That just doesn't work. Write your statements for K. I'm going to come around and check and see how mathematically you write. Love it, King. Implies. Right, see? Several people are saying that. Oh, yeah. All right, hook it up. What do I write here? K greater than 0. What does this symbol mean? This symbol? Implies or then. So if K is greater than 0, what did it do? How far? Can I not say units and just say up K? What's an up K? There's a joke in there somewhere. Other side? Hey, what happens if K is less than 0? Hey, it goes down K units. All right, you guys, we're going to play the democracy game real quick. We have C knocked out and K, all of our translations. Are we going to do basic example with just translations left and right? Or do you want to get all of our transformations knocked out and then we'll do examples that can draw from all of them? All the transforms and then several examples? Good with it. All right, so we can translate. I'm good. Left, right, up, down. What else can we do? Side to side, I would say, is the same. We can dilate it. Okay, well, let's go ahead. We're going to change different language. I like that idea of dilation, but we are going to use more formal language with it. All right, translations knocked out. It's C and K inside of the parentheses. All right, so instead of dilation, we have different language because dilate doesn't quite work like it does if you have a circle that's getting bigger and smaller, but we can't graph circles and call them functions. So we have compression, compressions, and totally lost my train of thought, I'm sorry, stretches. Now, for these guys, we have two situations. With parabolas, it's really easy to think thinner or like wider or thinner. Like that's a natural way to think about parabolas. But are there functions that aren't parabolas that we could still think of compressing or stretching? Probably, right? So check it out. What I'm going to show you guys, we're going to stop him for a second. Compressions and stretches. Quadratics are nice. What's the easiest cubic function you guys know to work with? X squared is the easiest quadratic. 1x squared. What's the easiest cube? X cubed. So if this is x cubed, I'm going to turn this one off. Okay, here's what the graph of x cubed looks like. If I notice, I didn't change anything except for how this is defined. Will C still move this graph left and right, you think? Cha-cha. Yeah, it still does the exact same thing. It doesn't matter what the graph is, so long as it's one of these nice functions. What will K still do? Up and down. All right. Now, as we look at this, we're just going to observe. We're going to check this out for a second. Which one should I move? A or B? A. So we'll do it here with the x cubed for a second. And I just need you to tell me, did it get thinner or thicker? Bless you. So green is the new one. That got thinner, right? So we just determined that that number A can change this, yeah? What if I go the other direction? So check it out. We're getting back to normal, right? So here's our normal one. If I go one little tick to like 0.5, wider? Is that indeed what happened? Okay, notice I'm stopping somewhere. What's going to happen if I go further? More on that in a few minutes. Okay, so seemingly A is the one that changes the compression or expansion, right? But hold up here, because I'm going to hopefully blow your minds here. I'm going to move B as well. Huh. Oops, we won't do that. Interesting. Hold on. I thought A made it thinner. B can make it thinner too? Huh. Now, there's issues with this. Like, obviously we can see what's happening. I like to think of literally standing on a parabola is how I think of these, because we can do two things. Imagine, I don't want to break a ruler. Do I? Nope, we're not going to break a ruler. Imagine I'm standing and my feet, there's a vertex, okay? Parabola. And then I'm holding onto the sides. If I pull inward right here, what did it change about the shape of the graph? It's gotten thinner, right? I have compressed this thing horizontally. Now, alternatively, if I say that I don't have a stretchy parabola, I grab the same points of the parent, and instead of doing inward, I pull straight up. Will it have to get thinner in order for that to work? So that's a weird thought. If you can't imagine that, I'll show you up here. I need a volunteer to come help me at the board for a second. Hey, you got it, Lily. All right. So you're my vertex. You hold this wherever you want, or just hold your end, and I'll actually be the vertex. So here we have a parabola-ish, right? So if we both pull inward, it does get thinner. Everybody cool with that? Now check this out. We'll go back to the original. What if, and I'll pick the same point over here, what if we both pulled up?
It would get thinner.
It got thinner as well. So we can do this two ways. We can either, thank you, we can compress it by pulling both sides in to make it thinner, or we can stretch it to make it thinner by pulling straight up. They look the exact same, which is why it's sometimes hard to identify. But if you don't have to tell me which way it happened, and you're just trying to get a good picture of a graph in your head, this is crazy helpful. Now, the rules can be hard to generalize. Let's look at that A value first. I'm going to make that B1, and let's just see if we can't lock this in. A, if A is big, did it make my graph thinner or wider? Thinner. So when I say A is big, I literally mean A is greater than what number?
0.
So if it's greater than 0, these are still greater than 0. Is it thinner? 1, right? So let's generalize. So 2 ways to do this. We have, just like we had horizontal and vertical compressions or translations, we are also going to have horizontal and vertical stretches and compressions. So let's go ahead and knock out. First, we'll do vertical. Okay, and just to make sure that I don't leave the notation or the style that we've been doing, I switched them. It's going to drive me crazy, but you guys have already written, so we'll commit to it. We did horizontal first before, right? Yep, that's going to drive me crazy. Hopefully not you. We'll be all right. So check it out. Here we are. If we change this vertical, and we're looking at this guy, we see that this is going to be our value of A for our graph. Okay, this is the one that tells me pull it straight up. Makes it thinner, right? Under certain circumstances. Same thing, we're trying to go kind of quick. If I'm going too fast, what do you do? Tell me, interrupt. If I'm going too slow, what do you do? If I'm doing just right, what do you do? Or compliment me, okay, all right. Here we go. What if A is greater than 1? What did that do to our graph if A is greater than 1? So it made it thinner. Now, because we're in the vertical situation, did that vertically stretch it, or did that vertically compress it? Which one makes it thinner, pulling up or down on the parabola? Up. So if A is greater than 1, what we see is this very specifically is just a vertical stretch. Now, we could say by a factor of A, but it's harder to envision what that one looks like. I'm going to make one more little change. I'm going to put these lovely vertical bars beside A. Means what? So one single is 1 is such that. I like that. What about if I put a number in here? I'm asking you to do the what? Absolute value. Okay. Now, we'll see why I'm doing that here in a second, but here's one situation. It gets thinner, and I'll even go ahead and just say thinner. More narrow if you'd rather. Okay. The natural other try is to say the absolute value is what? So one option is greater than 1. Less than 1. Now, 2 ways you can present this. And I don't care which one you do. I think that this one would suffice for now. But just so you're aware, in red, the other way, we can think about this. If we're talking the absolute value, this would require that 0 is less than a, which is less than 1. These are the same statements. One with absolute value, one without. They mean the exact same thing. Cool. What happens if the absolute value of a, or just in general, a that we saw in our graph, was between 0 and 1? What does it do? And I'll go back to that screen in a second. Between 0 and 1, it does what? So I'm okay with bigger. Is wider okay? And if we're doing this vertical, if I have this parabola and I want to make it wider, do I need to grab this point and push down or pull up? Push down, right? And we know pulling up is like a stretch because I'm stretching it. What do you think we're going to call that pushing down? Based on what we've said today. Could be gravity, but math doesn't care about gravity. Hey, it's a compression. So check it out. Here we go. Easy to say. If a absolute value of it is less than 1, this tells me a vertical compression. I didn't specify, but shot in the dark, what is vert short for? I'm cool with that. Vertical compress. Which did what to the shape of it? Thinner or wider? Wider. Cool. Two situations that make my graph either thinner or wider. Now, we also can do this in the horizontal direction, but things switch. And it feels weird that they switch, but when we think about it like physically grabbing a parabola or whatever function, I think this is a little bit clearer. For our horizontal changes, instead of being outside, which is where this a lives, a times f of x, we are looking at this b value on the inside. Again, do the letters really matter? No, and I don't have a good way to alliterate what these do, but here's what I want you to do. I'm going to let this play, and we'll go back to x squared because I think everything is easier to see. I'll tell you, if we mess with the inside, we are doing horizontal stuff. So I'm going to let this thing just go, and my challenge for you guys is we're going to slow that way down, first of all. Can I slow it down? I don't know. What do you guys think? If I step by something really tiny, maybe. All right, we'll save that real quick. Go. What? Cancel. All right. I want you guys to decide as this animation goes. I'll give you a minute. I want you to write me my two statements. If b is greater than 1, if b is between 0 and 1, what is happening to my graph? So you can see when it's thinner now and b is there. Talk it out. I'll give you about a minute. I want to see what you come up with. If you want to write it in your margin instead of committing to the page, I'm good with it. We'll generalize it. Okay. So check this out. You're going to be able to look there. Thinner. What's value Sorry, I'll be right back, Kennedy. All right, I don't want us to have to worry about the negatives, so I'm going to get rid of those real quick because I didn't realize that they were there when I first did it. Because it can be kind of hard to pick out. So let's go 0, and we'll go to 10 so we can get a big enough piece. All right, now let's let it ride because the negative does something different. So check it out. Right now, am I thinner or thicker? Thinner. You can probably write a statement with that. Horizontally, if I want it thinner, do I stretch it, like push it out, or do I compress it, pull it in? We compress it. I want you guys to generalize what values of b change, just like we have been doing the other ones. I'll give you about 60 seconds, and then we'll come back together as a class and see if we can write it all together. Do you guys know what the margin of your page is? Okay, I'm going to nerd out on you for a second. I'm going to teach you a new word. I'm going to steal this for a second. Okay, anybody ever heard the term marginalia? Probably not. Okay, me neither until, I don't know, randomly. This is the margin of your page. Whether it's drawn or not, this is what it's called. If you are doing like doodles or little scratch work or something in the margin of your page, it is referred to literally as marginalia. When I ask you guys to write your statements, if you don't want them in the middle of your notes because you don't want to have to erase it and have it be sloppy, just always work in the margins, do your marginalia. It's okay to have stuff on the side. You should have stuff on the side. It shows you're thinking. Cool with that? All right. In your margins, if you're not confident, I want you to write me these generalizations. What happens when b is greater than 1. What happens when b is between 0 and 1? That's our focus. So listen. If b is like what's in it right now, what's value greater than so it's 7, still thinner, still thinner, still thinner, still thinner, still thinner. Why? Very easy. Notice we're thinner when b is as we get really close to 0, like now the graph is really flat. We see that horizontal here.
If B is greater than 1, if B is greater than 1, it's a horizontal crest. It gets smaller when it's larger than 1. But when it's
Whichever way you go,
B
is greater than 1.
if B is less than 1, it's for
I'm holding it for that one. I want you to
I mean, a horizontal. Here, I'll write it down in your horizontal. No, it's easier with the visual.
in the end, whether it's thinner or which is the same thing for 0 to 1. So greater than 1, huge, right? Like, what about between 0 and 1? Like, don't look at the number, I'll tell you. Right, thinner or more. So it says compressing. Or we stretch it out. The other side. All right, help me out here. Anybody struggling? Is it okay to struggle? Yeah, absolutely. So I'm going to pause right now. I have a small b value, seemingly, like not there. But if b is greater than 1, what did it do to my graph? Thinner or wider? Thinner. So using this language, we'll just go ahead and see if we can't summarize this real quick. Anybody is cool to just shout it out, but I want to know that if the absolute value of b is greater than 1, it made it thinner is what you guys just told me. Which of these two words is that? Compress. Now it's like we're grabbing the parabola and we're pulling it in. We're compressing it together. It should get thinner in that situation. So here we go. Horizontal, H-O-R-Z will be my shorthand for that. Compress. And notice that it changes. It was a stretch for A. It's a compression for B. What's the other side of this statement? Should we change that because it might make us giggle every time? Okay, never mind. Nothing. Cool. Absolute value of B is less than 1. What's that going to do? And horizontally or vertically? Horizontally. Horizontal stretch. Okay, which one was thinner? The compressed, right? Cool. We'll say thin, thick. All right. So we're getting wild in here. We're moving left, right, up, down. We are getting thinner, wider, steeper, less steep, if you want to word it that way. Again, just so we can see it, I want us to verify that even if it's not x squared, doesn't matter, we can pick a super ugly function. X, we won't pick a super ugly one yet, but x cubed. If I let b be large, did it make that thinner than the other one? Or steeper, if you would rather? Yeah. Does it get wider out here? Okay, we're generalized then. We've knocked out translations. We have knocked out compressions and stretches. Is it possible you think that we can't tell for sure whether it's been vertically stretched or horizontally compressed? If I just give you a graph and you see it's thinner, you don't know for sure which one it is. That's okay. We just know that it's changed. All right, what's the only transformation that we haven't seen? Reflections. Okay, these ones are hard to see if we use a quadratic, but let's not use a quadratic then. That's easy. Reflections. Now, these ones are a little bit weirder to generalize. There are only two lines that we're going to reflect our functions over, for now anyway. Any ideas? The x-axis, so we'll have x-axis reflections, and we'll have y-axis reflections. If you guys recall working with parabolas and quadratics and stuff, you know that every parabola does have a line of symmetry that it reflects over. We'll get to all that eventually. All right. X-axis and y-axis. Thoughts on what I should try to change to get this thing to reflect? Don't care if you're wrong, but give me something to try to change. A? All right, so if I change A, let's just take a look. And I'm going to go back to this one for now, and we'll come back to the other one. X squared is what we'll look at here. So A, has it reflected yet? No. When will it? Hey, if I go negative. Now, here's why we've used the absolute value stuff. If I pick negative 0.4, look at your sheets on your notes. If A is between 0 and 1, its absolute value, should that make it wider or thinner? Check your notes. A between 0 and 1. What did we just conclude about that a second ago?
Wider.
Hey, it should be wider. Is this wider than the original one, the red one that we started at?
Yeah.
Okay, so it still works whether we reflect it or not. If A is negative, though, I see that there was a reflection. What do we reflect over? So check it out. A is this x-axis reflection, and I'm not going to put A here like we have been because it's more associated in my mind with these vertical changes. However, we're just going to make one little easy statement. I don't know why I would change color. A less than 0 implies we do what? Reflect where? Reflect over x-axis. Okay, that one is really easy to see, especially with pretty much any of the graphs that we deal with. If A is less than 0, reflect over the x-axis, but we still worry about the stretch and compress. All right, one more. We're going to get crazy with it. We have our lovely quadratic. Thoughts on what I should possibly change here?
Can you do that?
I can. If A is less than 0, we reflect over the x-axis. And I think it was Lando. Was that you? I don't know. Somebody said B. I don't know who said it. Okay. Or I heard it. I don't know. You good, Kenny? Thank you. All right. So we need to reflect over the y-axis somewhere as well. What should I change? Everything else, I just want to set it back to what it normally is. So it's normally 1. Here we go. Okay. So now everything's the same, right? That's just our parent. Can I change B and get it to reflect? So it gets thinner, we've already seen that. Gets wider, we've already seen that. Oh. Could you tell it did it? Probably, like, maybe. It's hard to see on this one though. Like, and I wanted to really emphasize that. If we pick a function that doesn't look quite as nice, and that's subjective, but if I do x cubed, for example, and now I change b, check it out. Positive 1, it's a regular old function. As I get here, it's getting wider like we were expecting to happen. But the second that I go negative, what does it look like it did? Over what? Bet. All right. So here we go. Easy to say. If B is less than 0, notice we can still make it thinner or thicker in this same situation. We don't care about the absolute value for the reflection. If B is less than 0, it did reflect, and it reflected over what again? Reflect over Y. All right, feeling kind of okay with it. First question that I have for you, just like legitimately as a teaching practice, is it okay to do it all on Desmos, or should I do this with my next Algebra 2 class? Should I make them all do this on their calculator over and over? Desmos is good enough for this, right? Okay, so for our starts here, we're just gonna play around with a few of these and kind of see where we're at. We have reflections, we have compresses or stretches, and we have translations. Being able to identify them and writing this stuff mathematically can make it look scary. It's not. Okay, so we're going to do a bunch of examples right now. I will have a short assignment for you. You won't have a ton of time in class. Sorry. Cool. Examples. Okay, for this example, I'm going to be kind of wordy with it, but we're going to say given f of x, given y equals f of x. So it's just some graph that's defined by this function f. I want you to do a couple different things. For this first one, we will state the transformations, and I'm just going to say transform needed to obtain a new function that we'll call h of x. Okay, so I'm going to give us a function f. I will give us a different function h, and you're going to tell me from f, that original function, how did we move it to get there? Did we go left, right, up, down? And we're going to do this without ever having to look at the graph, which can be pretty convenient if you don't love graphing. Okay, so let's dig in. We want start super hard, right? Okay, good. Baller. All right, let's get wild with it. On A, let's say that we have f of x is this lovely absolute value of x. Gosh, what did that look like again? Like, we're not graphing it, but what does it look like? Absolute value? I don't have a stutter, and I was not unsure of my answer. The absolute value? It's a V shape every time. That's it. So here we go. Here's our regular old parent function, the simplest of this form. We're going to consider the following. h of x, our new function, and I'm going to write this middle part we can talk about. We'll have to make sense of it. But I want 2 f of x minus 1 plus 3. Right off the bat. On a scale of 9 to 10, how stressed does this make you when you just see this problem here? Does it really stress anybody out? Notationally, sorry? A 6 or a 7 on a 9 to 10 scale? Okay. Anybody else catch the goofy thing that just happened? I picked a randomly arbitrary scale. Okay. All right. This is ugly. Do we know what f of x is?
Yeah. No.
Are you sure? Hey, it's this. According to this, my new function, what goes in front of f of x?
2.
Okay, deal. So easy. We're going to write out what this actual function is. And like this is how the problem would present, and then it is our job to make sense of the rest of it. So we get a 2 times f of x was the absolute value of x, right? But we're going to go a step further. In the function f of x, here's the only x in the whole thing. What did I replace x with on this one? There was an x in this parenthesis. What's in there now? More than minus 1. Not just minus 1. Some of you said the right thing, some of you said the wrong thing. It is not just negative 1. What's in these parentheses? X minus 1. Okay. I will refer to whatever we're taking the function of as the argument. And we'll see this word show up over and over. This is the argument of my function. What's inside my parentheses. So if I replaced the x with x minus 1, that just means anywhere that there's an x here, what should I replace it with? What did we replace it with here? What's the argument? So what should I replace it with? Boom. X minus 1. Are there any other x's in my original function f? No. Is there anything else that I need to put here? Plus 3. So we've done 2 things we've practiced with. One is making sense of how we write this out and say, oh, look, we're basing h on f, some other function that we started with, the easy one. I want you guys now to tell me the transformations that have happened. That's my goal. Together as a class, or do you want to try it individually with your small groups first? Okay, so check it out. I don't have all my notes in front of me. Are you guys still on the same page that you have been all day? If not, can you turn back a page? Hey, look at that. Gosh, this is what, and you don't have to label this the exact same if you don't want to. Is this A, B, C, or K? If it's outside the function, A. All right, what is this? So I'm going to say A equals 2, and I'm just identifying these. If you don't need to write this, don't. Yeah, like we'll make sense of them. What variable is this from our generalized function? X minus C. Okay, so what is C equal to in this situation? 1. Because it shows up as X minus C. This is X minus 1. Okay, C is 1. What's this thing? And K is equal to, I don't think this one's a shock, it's 3. Okay. If I don't worry about the negative, because there's no negative here, did this thing reflect over the axis? Over either? No, because it's not negative. Okay, so this is going to have an impact. If A is greater than, or if A is equal to 2, is 2 greater than 1? I think so, right? Yeah. What does a greater than 1 do to your graph? Makes it bigger. What do you mean bigger? Thinner. So compress by a factor of what? Good. So it's twice as thin, which is a weird thing to think about, but we'll look at that. What did this one do?
To the right.
How far? So we move right 1 unit. What else happened? Louder? It went up 3. As long as we can get to here, and whether you can get to here or if I give you this, my main goal is for you to be able to make sense of this. Can you guys imagine what this looks like? F of x equals root x, or sorry, F's value of x. So check it out. I'm going to do it really quick and not much effort. You guys do not have to draw this. The original function f is just a v shape. I'm not even going to put a scale, just so you guys know. Okay, but check this out. Here's what absolute values look like. You don't have to draw this. I'm going to check it on Desmos as well. You can, obviously. This is f. Okay, there's no scale anywhere. How did we move it? So it got compressed, so it's thinner, yeah? So it's twice as thin or half as wide, which is a weird idea to think about. Any other movement?
Right.
So check it out. If I pick any arbitrary point, and I'll do this one in red. If this point was on F, can I move this right 1 unit? And in fact, every point would move right 1 unit. So I would have now a V shape right here. Okay, it's gotten thinner. So when I draw this, it'll be a thinner one as well. Any other movement? Up 3. So I don't know where that is, but maybe it's here, yeah? Okay. I then see that, hey, if I know that V shape is my original, here's a thinner V shape that's been moved right 1 and up 3. Does that seem reasonable? Okay. If I asked you to graph this by making a table, it would take a little while, right? But if all you need to know is like some general stuff about the graph, this would be enough. Let's check. You guys are going to have to help me because I already forgot all those numbers. Absolute value of x. Okay, there's the original. What did we change about it? This was 2, right? We'll just go here. We had 2, so y equals 2 times the absolute value of x minus 1 plus 3. Gosh, did that get thinner, move right 1 and up 3? Was my graph perfect?
Yeah.
Thank you. Not really, but that's okay. If all we're doing is wanting a good idea of where this graph is, we have it. Okay, here's my challenge for you. For homework stuff, because I don't have textbooks for everybody until you guys all have access to the online stuff and some people return books, it's going to be worksheet mode. Okay.